Hi everyone and welcome back to the third module Static Detection Bypass in the Visual Lab course by Altered Security. Now let's take a look at the first static detection bypass techniques, which is LLVM obfuscation. So what is LLVM obfuscator? The LLVM obfuscator is a set of techniques designed to make code more complex and harder to analyze while preserving its functionality. This is particularly useful for protecting software from reverse engineering, unauthorized modifications, or intellectual property theft. By transforming the code structure, obfuscation makes it significantly more difficult for defenders to understand how the malware works. So there is three main reasons why obfuscation is used. First of all, intellectual property protection. So it helps companies prevent their own code from being stolen or copied. The second is security against reverse engineering. It adds an extra layer of defense, making it hard for attackers or people that are trying to understand the code's logic from analyzing it or exploiting it. And third is mitigation static analysis. In case of malware development or security research, obfuscation complicates automated analysis tools, which is useful for those cases, the malware development in our case. In short, LLVM obfuscator is a crucial tool in software security and in malware development, whether to protect legitimate software or to evade detection in our case. So now to use obfuscator, LLVM, we will, within Visual Studio for sure, we have to follow these steps. Before setting up LLVM, ensure that Visual Studio is installed along with those components. First of all, download and install Visual Studio, preferably to be 2022, if not installed, from the Visual Studio official site. Second, open the Visual Studio installer and modify your installation to include desktop development with C++ under the workloads, and under individuals components, add the CLang compiler for Windows and MS build support for LLVM CLang CL toolset. Once Visual Studio is properly set up, you need to integrate OLLVM. So download the precompiled OLLVM binaries. We're using the version 13.0.1. So download it from our static detection bypass resources folder and navigate to this following directory: C program files, Microsoft Visual Studio 2022 community VC tools LLVM x64 bin, and copy and paste those binaries into that path, into this directory. After placing the OLLVM binaries in the correct directory, you need to configure Visual Studio to use them for compilation. So important things here: you have to ensure your project is a pure C, and OLLVM only supports C. So if your project contains C++ syntax or headers, you will get errors. So replace C++ headers like EOStream header with studio.h header. Avoid any C++ specific features such as classes, objects, namespaces. Now to configure Visual Studio to use OLLVM, open Visual Studio and load your project. Right click on the project, go to properties. From the Solution Explorer, go to properties and general, and change the platform toolset to LLVM CLang. Click apply and OK, and go to C++ to add the obfuscation flags. So you go to C++ command line, and in the additional options field, add obfuscation flags depending on the level of protection you want. So for simple obfuscation, we have this command: which for each one it defines, for example, for dash x clang dash f legacy dash pass manager, it ensures that LLVM uses the legacy pass manager, which is required for OLLVM obfuscation. And for the flag dash mllvm dash sub, which refer to instruction substitutions, it replaces simple instructions with more complex equivalents, making the code harder to analyze. And for the flag dash mllvm split dash split, which refers to control flow splitting, it splits basic blocks into multiple smaller blocks by including multiple conditional jumps, increasing control flow complexity. And for the dash mllvm dash fla, which refers to control flow flattening, it converts a linear control flow into a state machine-like structure, making execution path less obvious, meaning instead of executing functions in a clear order, all functions are controlled by a state variable. And for dash mllvm dash pcf, for bogus control flow, it adds fake conditional branches that do nothing but confuse the compilers and disassemblers. Now let's take a look at the heavy obfuscation and the extra obfuscation flags that it has. So for these extra obfuscation flags, we have dash sub loop tree, which repeats the instruction substitution 3 times this, making the transformations deeper and harder to recognize. And for dash split num, this, it ensures each basic block is split into 3 smaller ones. And for dash bcf prop 100, it ensures that 100 of all conditionals are obfuscated with bogus logic. And for dash bcf loop tree, it repeats bogus control flow insertion 3 times, increasing complexity. So now let's take a look at the difference between the Microsoft Visual Studio compiler and others versus the OLLVM compilation. So standard Microsoft Visual Studio compiler generates a straightforward executable, produces readable machine code which with a clear control flow, easy to analyze using like IDA, Pro or Ghidra, and the decompilation is easy, making static analysis simple. Now in other side we have OLLVM compilation, which applies advanced obfuscation techniques at the compiler level, making reverse engineering extremely difficult by breaking normal execution into execution flow into state-based execution, making function trace hard, and injects fake conditions and jumps that confuse the compilers, and replaces common operations with equivalent and complex alternatives. So the decompilation in this case is extremely challenging due to complex control flow. So how OLLVM breaks signature and static detection? As static detection and signature rely on patterns in assembly code, so OLLVM obfuscation significantly alters instructions sequences, breaking detection rules. So malware compiled with OLLVM will often evade static detection, as antivirus and EDR rely on known code. So now let's take a look how we could compile a project with OLLVM. So refer to the static detection bypass folder. You will find those 2 projects. They both use the same code, which is message box test, and the only difference is the compilation, the compiler that we will be using, either CLang with OLLVM or the Visual Studio compiler. So in this case, we're using the Visual Studio compiler, but let's take a look how we could set up OLLVM. So we go to these project properties, and under the general, we have to modify the platform toolset to LLVM CLang, from Visual Studio to LLVM CLang. And under C++, we go to code generation, and we set the runtime library to multi-threaded MT. So to ensure that the application statically links the C runtime library into the executable. Otherwise, you will get errors while using this binary outside your environment, development environment in other machine. So in the command line, make sure to add the obfuscation command under the additional option. And now press build to build the two projects. I already built them, and load them to IDA so we can see the difference. We can see that Microsoft Visual Studio compiler produces readable machine code with a clear control flow, and if we press F5 we can see that it's easily decompiled by IDA. The other hand, you can see that the OLLVM significantly significantly makes the compilation extremely challenging by introducing a complex control flow and breaking signature to bypass static detection. You can see a lot of branches here and a lot of blocks, and this is the entry point, and from there it prepares the API for message box, but we can bypass that by doing some API hashing and hide that and resolve it dynamically, not statically, as you can see here. And we cannot see the call to the message box, it's inside somewhere here. So let's try to press F5 to decompile it in this case, and we can see that the compilation it's extremely hard. And we can see here we have a lot of branches and blocks, and even the code is very, very, very long. Hi everyone, and welcome back to the third module, Static Detection Bypass, in the Evasion Lab course by Altered Security. Now let's take a look at the second static detection bypass, encryption and native PE loading, and more specifically, local hollowing technique. This execution flow showcases in memory PE execution. Now the diagram follows 4 key stages of mapping an encrypted Mimikatz binary into memory without writing it to disk. So the first stage, we have process.exe, which is our process and its own main thread and a new created thread. This process contains also in its address space an encrypted Mimikatz and its ES key that will be used later to decrypt this Mimikatz. And in the second stage, the main thread is temporarily paused, meaning suspended, by the newly thread, and this newly thread will decrypt the encrypted Mimikatz using the ES key. The encrypted Mimikatz binary is decrypted in memory, but still not yet mapped for execution. So in the third stage, a dedicated memory region is allocated by the newly created thread, and its size is the size of Mimikatz.exe, the decrypted one. Then the newly created thread will map headers and sections from Mimikatz.exe into this newly allocated memory. Now the newly allocated memory will contain the headers and sections. In the fourth stage, the new thread will apply relocations and load importers. The base relocation table is processed to fix absolute memory addresses, ensuring the PE can function correctly at its new memory location. And the import address table is patched by resolving external function dependencies, allowing the PE to call system functions. At this phase, The new thread will then modify the thread context of the main thread so that execution resumes at the entry point of the mapped PE after locating its entry point, meaning that this new thread will make the instruction pointer of this main thread pointing to the located entry point of the mapped Mimikatz in memory. So after resuming it, the process console will be changed to Mimikatz console, and we will see the Mimikatz signature on it. So far, we've discussed the theory on how a portable executable can be manually mapped into memory for execution. Now, instead of just discussing the concept, we are going to see the process in action using actual code. In fact, just an overview on the used code and the implementation. We will see the entire code in depth later. The first thing we need to do is gain control over execution before modifying memory by suspending the main thread. And to do so, we have to gain or obtain a handle to the main thread by calling get current thread API. Then using that main thread handle and duplicate it using the duplicate handle to get a duplicated handle of the main thread to use it later in create thread. In the create thread API, we'll be using the duplicated handle to launch a new thread, and using that duplicated handle to make the newly created thread suspend the main thread later. So we call suspend thread, and we use the main thread to suspend it from the newly created thread. In this phase, the main thread is suspended, and we control the execution using the new thread. So the new thread will decrypt, in this case, the PE and validate it later. To do so, we will call crypt acquire context that will initialize cryptographic context and functions, and call crypt create hash and use the decryption key that we have and generates a hash, a hash using the SHA-256 algorithm. Then we use that hash to generate an EES-256 key for decryption using the crypt derive key API. And after that, we will be using this key to decrypt the PE buffer in memory, which is a Mimikatz in our case, using the crypt decrypt API. After making sure that the PE buffer is decrypted, we will validate it and ensure it's a valid PE by checking the DOS and the entry header of that decrypted PE. And if it's valid, next we will allocate size of Mimikatz memory and map the headers and sections and apply base relocations to this allocated memory to this mapped PE in the allocated memory. So we call virtual alloc API to allocate memory equal to the PE size of image, which is the Mimikatz size of image, with the protection page of protection memory of page execute read write. So RWX memory protection. Then we call mim copy API to copy the PE headers and sections into that allocated memory. After that, we process a relocation table to adjust the memory addresses to fit the new memory layout. Why we are doing this? Because the PE expects to be loaded at a specific memory address. If it's loaded elsewhere, absolute addresses inside the PE must be corrected. At this point, the PE is loaded into memory, but it cannot yet execute because it depends on the external system functions. This is where resolve imports come to place. We will call later load library A to load the required external libraries that this PE is using and depends on. Then we call getProcAddress to resolve function addresses dynamically of those DLLs, that those DLLs are exported. And we patch later the image import descriptor and image thank data structures to update the import address table with correct function addresses. Why we are doing this? Because most PE files do not contain all their own code. They rely on system libraries for functionality. Without resolving imports, the PE would crash because it wouldn't know where to find necessary functions. Finally, we need to redirect execution to the mapped PE and let it run. So this is where the set entry point and resume execution come to place. So we call get thread context to retrieve the current execution state of the main thread. And we modify the instruction pointer, the RAP, in the x64 architecture to point to the PE's address of entry point, which is the main. And then we call set thread context to apply the new execution state and resume the thread to resume the execution inside the mapped PE, meaning that the main thread will be executing the entry point of the newly mapped PE, which is Mimikatz in this case. Why is this important? Because the current execution flow is still pointing to the suspended thread. So we need to redirect execution to the new PE's entry point, allowing it to run inside the hijacked process. So what are the key advantages of this technique, local hollowing? First of all, there is no disk writes. The PE is executed entirely from memory bypassing file-based security scans. Second, there is no new process creation. The PE runs inside an existing process, avoiding any suspicious process creation logs. And also there is no new thread creation and no new image loading. It's a stealthy execution flow since we manually control execution and we don't use the PE loader, the built-in PE loader. So it becomes much harder for security tools to detect this technique. Hi everyone and welcome back to the third module, static detection bypass in the Visual Lab course by Altered Security. Now let's take a look at the local hollowing technique. So in this Mimi.h header, we have the cipher Mimikatz and its CS key that will decrypt it to get the raw Mimikatz. So we included that header in the top, so we can use the cipher PE buffer that contains the encrypted Mimikatz and its key to decrypt it later. Now let's go to the main. And the main, it's actually will duplicate the current thread, which is the main thread, then creates a new thread that will execute a function that will execute a new thread that will execute a function that will actually suspend the main thread and do the heavy work by mapping the entire PE and fix it in memory and trigger the entry point to run Mimikatz. Then wait for the thread execution to complete. So first of all, we call get current thread to get a handle to the main thread and store it as pseudo handle. Then use duplicate handle and use the main handle to get a duplicate handle for that main thread handle. So the duplicated handle of the main thread will be stored in the real handle. Then we will call create thread function to execute this doit function and pass as argument the duplicated handle. Now let's take a look at this function. What this function will do actually, it will suspend the main thread, decrypt the encrypted Mimikatz using the key, the ES key, and run the decrypted PE in memory by mapping headers, sections, apply relocations, and fix the import addressable and trigger the entry point. So this function will take the duplicated main handle and using later suspend thread to suspend the main thread, so we function just with the newly created thread. This newly created thread will do the entire work, starting by decrypting the encrypted Mimikatz, and we pass to it the PE buffer which contains the cipher Mimikatz and the ES key that will decrypt the cipher. So let's go to this function. And what this function will do is actually will decrypt the Mimikatz PE file using the ES256 algorithm. So we call first of all crypt acquire context W that will initialize the cryptographic provider and initialize the cryptographic functions. We'll be using prov RCAS variable to make sure that we're using the ES algorithm provider. Then we call crypt create hash to create a SHA-256 hash object. Then using that object to hash the decryption key into the SHA-256 hash. So we hash that decryption key, and after that we will be using this hash to generate a 256-bit ES key from that hash. It will be stored in this key handle, and after that we decrypt the cipher using this key handle. So we decrypt it into a Mimikatz raw format. Then we do some cryptographic handles cleanup, release the cryptographic provided by execution crypt release context, and execute crypt destroy hash to destroy the SHA-256 hash objects, and crypt destroy key to destroy the ES key to avoid any sensitive information leaks. Now let's go back. And in this case, the PE buff, the cipher is decrypted and we have a raw Mimikatz. We check if the Mimikatz is actually not null, and if it's not null, we check the validity of the PE, if it is actually in an actual PE format. So let's go to this function to see how it's working. The Mimikatz is pointing to the DOS header, and from the DOS header we get this il-fanu that is contain the RVA of the int header. Adding the RVA to the DOS header, we get a pointer to the int header, and from the int header we get this signature field and check it against this value PE00, and if it's true, the PE is valid, and we continue. Then if it's valid, we print that the PE is valid. We print the address of Mimikatz in our process memory, and then we run this PE function that will take the main thread handle, because we will be using it later to make it point to the entry point of Mimikatz and resume it, so it will run Mimikatz. So let's go to this function. What this function do actually, it will map the headers, the sections, apply relocations, resolves the import address table, and then execute the entry point of Mimikatz. So Mimikatz is pointing to the DOS header and getting the RVE of the entry header added to the DOS header to get the base address of entry header. We check if it's valid, then we allocate the size of Mimikatz, and the allocation memory is committed and reserved, and RWX, read, write, execute. After that, we check if the allocation is valid. If not null, we copy the headers because the size of headers exists in the optional header structure that is embedded into the entry header. So we copy size of headers from the Mimikatz into the newly allocated memory. Then we use this macro function to get the first section header of the PE, and we access the number of sections inside the file header, the embedded structure in the entry header, and we go through each section and we map it into the allocated memory using this line of code. So this line of code will map each section, and we iterate over each section to map it to the newly allocated memory just after allocating mapping the headers. After that, we get the RVA of the relocation table stored here and check if it's valid or not. After that, we get the base address of the relocation table by adding the RVA of relocation table to the allocated memory. After that, we go through each block in the relocation table and check if the last block is null. If it's null, we finish all the blocks. So for each block, we get the RVA and we check if its size is valid. Then we determine the number of entries in this block, and for each, and then we get the list of relocation entries that contains the relocation offsets and types in this block, and we go through each entry, check the type of the entry, it is valid or not, and get the RVE of the entry using this line of code. Then get the original address of the entry and then adjust it to this allocated memory by subtracting the original image base and adding the new base, which is make it adjusted to this allocated memory instead of the original entry address. So then we go through each relocation block and do the same to fix this relocation entry and make it adjusted to the allocated memory. After that, we get the RVA of the import address table. We get it from this directory, data directory table. So we get the RVA of the import table directory. We check if the import table directory entry is valid. Then we use that RVA and add it to the allocated memory to get the first import descriptor, which is the first import descriptor that contains the first DLL. Then we go through each DLL and check if it's valid or not, if it contains a name or not. If it's valid, we get its name by adding this import descriptor name to the allocated memory. We get the module name. We use load library to load that module DLL by name, and it will return the address of that module loaded into our process memory. And if it's loaded successfully, we get the first thunk, which is a pointer to the import address table that contains function pointers that must be resolved. So after getting the first thunk, we added this is the RV of the first thunk. We add it to the allocated memory to get the base address of the first thunk, and we shake its address of data inside this structure. We will loop, meaning we will loop for each function in that module, and we check functions by ordinal. If the function is imported by ordinal, we resolve by ordinal, and if the function is imported by name, we resolve by name. So we get the ordinal from this structure that is embedded in the thunk. Using this macro to get the function ordinal, and if we get it successfully, we resolve it. We get the function address using get proc address, using this ordinal. And if the function is imported by name, we use the name. We add the address of data to the allocated memory to get the function name, and we use get proc address to resolve the function address by function name. And after that, we fix the import address table of that function, meaning the thunk, the function inside the thunk is structure. So we store the resolved function address inside this thunk function, and we go through each thunk, meaning move to the next function in the import address table of the current module, and we move to the next module DLL in the import address table, and do the same by fixing the address, the function address in the import address table. After that, we create a context structure to manipulate thread execution. So the context structure holds register values in the execution stage for a thread, and we use context full to retrieve all register values. After that, we use get thread context to retrieve the current register state of the handle, which is the main handle, because we're passing the main thread handle to that to get the current register state. And if it's valid, we access to the REP and make it point to the address of point, which is the entry point of Mimikatz that is allocated in our newly allocated memory. And after that, we set the thread context so execution starts at the new entry point. So we make the context. We set the thread context to the modified one that contains the IRP pointing to the address of entry points, and then we add a delay execution to avoid any immediate detection, and after it we resume the main thread so it will run in the entry point. So run.ph will be running here and finish, and we return back to, and here the thread will be finish execution to do the do-it function, and we close the thread handle and finish the main execution, and the program will close. Now it's time to see the difference between this local hollowing technique and a raw Mimikatz drop into disk, and this local hollowing technique by running Mimikatz in memory, mapping it in memory. So first of all, let's drop this Mimikatz on this machine. Before that, this machine contains MD and Windows Defender. To check that, we type this command ps and msmpeng. That's the core process for Windows Defender. This process is running, and let's check also mssense, which is the core process for MDE. It's running as well. Now let's drop the Mimikatz, and it's detected. Now let's check the log for that machine. That machine is actually, who am I? It's this machine is SAT2. So let's go to the alerts and check the time, which is 11:30, around 33 p.m. This date 3/15/2025. So let's inspect the alerts at the most recent ones. Let's give it some time. So the alert got logged and printed on the dashboard. I will stop the video whenever the alert is appearing. Amazing. Now the Mimikatz credential theft tool is locked, and we got an alert at the same time, 11:32 p.m. Now let's prepare this mimi.h. All right, and prepare it. So for that, let's access to our projects, open a CMD on that folder, refer to evasion course projects inside the static detection bypass, and flange python es and mimikatz.exe. And what this es script is doing, it will simply open the Mimikatz as read binary byte and generate a 16 bytes random key, and use this es encrypt function to generate the cipher and the key, and drop him to the current directory as cipher.bin and key.bin. So let's generate the cipher and bin, and they are generated successfully. We will use hex editor, refer to the evasion tools folder to find the hex editor, and load this cipher and key to the editor. All right, Now let's click on File, Export C, and generate the key.c. Also for Cypher, go File, Export C, and generate Cypher.c. Good. Now let's go to the local HoloWin and copy this mimi.h and paste it here to modify it with this key and Cypher. Open it with Notepad and change both the content of key buffer and the content of p buffer and the size as well. So let's open this key in Notepad and change the content of mimi.h with that key. And change the Cypher.c content as well in the mimi.h. So we go to Mimi and change this content of the Cypher with the updated one. Now it's updated. Please make sure that the size is similar. Paste and save this mimi.h. Now let's copy the updated mimi.h to the project, replace that mimi.h, the past one, and open the local HoloWin Visual Studio solution to build the projects. We will use OLL-VM to compile our code and generate the obfuscated local HoloWin.exe. Alright, now the mimi.h is updated. Now we access to the project's properties and make sure that platform toolset is set to LLVM. The C++ code generation runtime library set to empty, and add in the command line the flags for the LLVM. Now press right click and rebuild the projects. It will take some time, so I will come back whenever it's compiled. Alright, the code is compiled successfully, and we can see that local HoloWin.exe, the obfuscated executable, is generated. So let's get it and copy it to the target machine that contains the MDE. And run it as administrator. So before run it, the time is 11:48. Remember that. So let's run it as administrator. It's not detected the Mimikatz in disk. So let's see if it's statically detected in memory as well. And we wait. The Mimi is decrypted and the PE file is valid. Then the PE will be mapped and loaded. The headers, the sections, applied the relocations, fix the import address table, and then trigger the entry point. And we can see that Mimikatz is running. It's not statically detected on disk and on memory as well, and there is no pop-up here for a detection. So remember, the time was 11:48. So now let's go to the alert dashboard and give it like 5 minutes around to see if Mimikatz got locked. Any alerts after 11:48 would probably be the detection for this local Halloween, and if we didn't get it, that means that the local Halloween is not detected. So I stop the video and I will come back after like 5 minutes. Now more than 5 minutes is passed. Now let's check the new alerts if it's after 11:48. And we can see that nothing logged after 11:48, and Mimikatz in local Halloween is not detected on disk and on memory, meaning that we bypass static detection successfully. Hi everyone, and welcome back to the third module, static detection, in the Evasion Lab course by Altered Security. Now let's take a look at this .NET encrypted PE loading technique. The first step is getting the encrypted .NET PE. This step focuses on how the encrypted .NET payload is obtained using network communication for PE retrieval. The process establishes a TCP connection using the following network functions. WSA startup. It initializes the WinSock library for networking. Get ADR info. Resolves the domain name or IP address. Socket. Creates a socket for communication. Connect. Establish a connection to the remote server. And finally receives the encrypted .NET PE file from the remote server. Next we did some memory allocation by calling malloc function. It dynamically allocates memory to store the received encrypted PE. The second phase is decrypting the .NET PE. Once the encrypted PE file is received, it needs to be decrypted before execution. For that, we are using the RC4 encryption. The encryption method used is RC4, a symmetric stream cipher. The decryption is performed by calling system function 032 from @VAPI 32.dll. This function is often used for cryptographic operations and is leveraged to decrypt the PE. The third step is AMZ and HEW bypass. To evade detection, the code bypass both AMZ, anti-malware scan interface, and HEW, event tracing for Windows. So AMZ bypass. For the AMZ bypass, AMZ is used by Windows Defender and other security products to scan scripts and executables for malicious static detection. Bypassing AMZ involves setting a hardware breakpoint on AMZ scan buffer, which is the function responsible for scanning the payload, and intercepting its execution and modifying its return value to AMZ result screen, which makes it appear as if the PE is safe. Then HEW bypass. So HEW is a telemetry and logging system in Windows used for tracing system events, including security-related ones. Bypassing HEW is done by patching HEW event right, the function responsible for logging events, and forcing it to return 0, effectively disabling security logging. The last phase is loading CLR, or loading .NET. After bypassing security measures, the final step is loading and executing the .NET payload. We do first the CLR initialization by calling CLR create instance, ECLR metahost get runtime, ECLR runtime info get interface. Those functions are called to initialize the .NET runtime. Then we start the CLR by calling ecore runtime host start. This function starts the CLR environment enabling .NET execution. And finally, we load and execute the .NET assembly. So AppDomain load tree loads the decrypted .NET assembly into memory, and method info invoke tree invokes the entry point of the .NET assembly executing the payload. Now let's take a look at the .NET decrypted PE loading with AMZ and HEW patching technique. Refer to the static detection folder, static detection bypass folder. You will find this sharp loader project. Now let's explain that project, going through the main. First of all, this main function will retrieve and decrypt and execute the .NET PE in memory. So first of all, it parses the command line to get the host, the port, the cipher file, the key file, and the base64 encoded argument. Then it decodes the base64 arguments and it retrieves the PE.NET cipher and its key, decryption key, from a remote server. Then it used its system function 032 to decrypt that cipher. And then bypass AMZ and HEW, and after it execute the decrypted assembly using CLR execution engine. So the first step is to get the arguments, including the host, the port, the cipher file, the key file from the remote server, and argument, the base64 argument for the .NET PE. Then we check the validity of the required arguments, if they are provided or not, and after that we base64 the argument. So after this moment, the argument is base64. Let's take a look at the function base64 decode, and this function will simply decodes the base64 encoded string into a raw string. So it's using crypt string to binary A to get the required buffer size that we want to decode. Then it allocates a buffer of size, the required size, plus 1 for null terminator. After that, it decodes the base64 string using crypt string to binary A, and this is the encoded string. It will be stored, the decoded string will be stored in these decoded bytes. After that, we add null terminate character to the decoded data, so it will become terminated. Alright, now at this phase the string is base64, and we used it get files data to get the cipher file and the key file from the remote server with host and port. Let's take a look at this function. Now the get files data function will establish a connection to a remote server and retrieves the cipher and key filelessly. So let's go through that function. First of all, it initializes this data structure to empty because it will contain the later the buffer data and its size. So this is the data structure, it contains a pointer to the received data and the length of that received data. After that, we XOR back this buffer that contains the get string but XORed, and when we XOR it back we re-obfuscate it to this get slash. Then we add it to this send buffer that will contain the entire request, get request. After that, we add the resource to our request. Then we obfuscate the resource to hide it from memory. After that, we create a buffer to receive the data, and we initialize the WinSocket to create the socket. After that, we resolve the server address and port using getAddr_info, and we attempt to connect to the server using this socket function to create socket for connecting to the server. After that, we connect to the remote server using the socket, and we send the request that we created, the get request, using the connect socket to send it to the remote server. After the get request is sent successfully, we shut down the sending side of the connection using the connect socket, and then we start receiving the response data from the remote server, the cipher and the file, the key. So we're using this receive to receive the data from the socket, and the received data will be stored in this RCV buff. Then we append this receive buff, the data that we received in this buffer, which is a vector of on-site char. We add this received data to the buffer, and we close the socket where we no more need the socket, and we check if the data is copied successfully to the buffer. After that, we calculate the size of the received data, and we allocate a buff data that contains the size of the data, and we copy from buffer to buff data the entire data, the cipher and the key, each time the function is called. Then we store the buff data and decide inside the members of this data structure that we saw before, and the function will return this structure. Alright, this file is data will return the cipher and the key. After that, we load the system function 032 to decrypt the cipher using the key, and we prepare the buffers for the decryption, and we call the system function that contains the structure for the cipher and structure for the key. And at this phase, the cipher is decrypted into .NET row.NET. After that, we set up AMZ bypass to prevent security detection. So let's access it and see it. So this will set up AMZ bypass by placing a hardware breakpoint on AMZ scan buffer. So we initialize a context structure which is used to store the state of the thread, the registers of the thread, and we load AMZ if not loaded yet. If it's loaded, we get its address. If it's not loaded, we load it using load library. After that, we get the address of IMZ scan buffer using get proc address, specifying the address of the loaded module and the name of the function we want to resolve. After that, we register exception handler using add vectored exception handler, and we register this exception handler. What this exception handler will do, will intercept the IMZ scan calls and modify their behavior. So it will make it return a clean scan. So first of all, we check if the exception is triggered, meaning that the exception is triggered by hardware breakpoints, and to see if the exception is occurred exactly on the IMZ scan buffer address. If yes, we retrieve the return address from the stack using this function, get return address, and we modify the IMZ scan result to indicate a clean scan using that, meaning that the result of the scan will be 0, clean. And we redirect the execution to the functions caller, meaning that IMZ scan buffer will not be executed. And we adjust the stack to simulate a return instruction. And we set the return value to SOK for IMZ scan buffer. And we remove the hardware breakpoint since we will not use it yet. After that, we set a hardware breakpoint on that's the exception handler. It's not triggered yet, but it will be triggered when IMZ scan buffer function is executed. So we set the hardware breakpoint to be triggered on IMZ scan buffer in this case. So after IMZ is bypass, we will bypass ETW as well by patching, by opening a handle to our current process and passing this handle to this function patch ETW. And what this function will do, it will patch the ETW event write that is used for writing events related to .NET and couple of user mod providers, ETW providers. So what this function will do, it will modify the first byte of ETW with ret instruction C3. That will effectively disabling ETW user mod provider. So we get the address of ETW event write from intdll.dll using get proc address, and this is the patch, which is a return instruction. So we use that to store the old memory protection, which is read execute, because it's inside the .text section, and we will change that first 10,000 in hexadecimal bytes in RX. This is RWX, sorry. It will be changed from RX to RWX using int-protect virtual memory, and then we use int-write virtual memory to write the first byte, to change the first byte with the return, so it will return. After that, we restore the original memory from execute read write to read execute, and in this phase the patch is successfully, the memory of ETW is successfully patched. After that, we convert this structure, this char array, into a vector of char. Convert the .NET PE to vector for execution, because this execute assembly method, it will just accept the vector. So we create an instance of CLR manager, CLR class, that we will see it later, and execute in memory the .NET assembly using the provided decrypted cipher and its arguments. So let's go to this function to see it in action. So this is our function CLR class, CLR. She's inside the namespace CLR manager, and this is the function execute assembly that will execute the .NET assembly from memory using CLR. So it will load the .NET CLR, this version, and creates and configures the .NET application domain, and loads in memory the .NET assembly, retrieves and invokes the assembly entry point, and then pass the arguments to the .NET entry point. So here we specify the target of the .NET CLR. After that, we create a CLR MetaHost instance to manage this CLR runtime using CLR create instance. Then we get the CLR runtime for .NET version 4.0 using this method get runtime. After that, we check if the CLR runtime is loadable using this method is loadable. Then we get the iCore runtime host interface to start and manage the CLR using this method get interface. After it, we start the CLR runtime using the start method here. After that, we get the default .NET application domain using the method get default domain. And after that, we get the IApp domain interface to manage the application domain using this query interface method. After that, we create a safe array to hold the assembly, and we copy the assembly to the assembly data to that safe array here, and we load the assembly into the domain, the .NET domain, the .NET app domain using this load tree method, and we retrieve the entry point of that assembly using get entry point. Then we check if we have an argument. We prepare argument for execution. As we don't have any arguments, this will be executed. Here we prepare the arguments. After that, we execute the assembly by executing invoke tree method. And we did, after the assembly is executed successfully, we did some cleanup. Now let's compile the project to generate sharploader.exe and refer to the script folder inside sharploader to generate the cipher and the key. Alright, now let's generate the cipher and the key for Rubius.exe. For that, let's execute Python RC4. This script will generate the cipher for Rubius, and it will simply use RC4 algorithm to generate the cipher and the key.bin. And here we have the key and cipher.bin. Let's copy them to the target machine that have MDE. Right. And let's copy the sharp loader as well. Yes, replace those. And let's paste also this sharp loader. So this machine contains an MDE. Let's check that. Run as, or maybe just normal user, but no problem. Let's launch PowerShell -c ps ms mpeng, and Windows Defender is running. And MS Sense and MDE is running as well. All right, now let's test with a normal Rubius to see if it will get detected. We will copy it. The sharp loader is not detected yet, but Rubius is detected. All right, I will stop the video so I come back after like 2 minutes so you don't get confused the detection of Rubius with the detection of sharp loader. So now we are in 12:23 AM. I will come back in 12:25 AM around. All right, it's logged after like 7 minutes, 5 minutes around. So this is the detection for the .NET Rubius, and it is this Kiko prevented. If we click on that and check the alert, we will see it's related to this Rubius. Let's go for the last one, which is this. When we drop the Rubius to the machine. So now let's go back and execute our sharp loader and set up the environment before run it. So the web server will be in our localhost. So let's run the server here. It's in Python. Right, and here we will access the desktop and run the sharp loader. It will use this command line. So those are the arguments: -h the localhost and -p the port, which is 800, -c for the cipher file name, -key for the key name, -a for the argument, which will be trees for Rubius. We will execute trees, sorry. All right, so it's Python, and we will use base64, and we will base64 trees. We copy that here and paste it. Let me paste it. Paste it. All right, let's recopy it. Right, so remember the timing. It's 12:32. I will execute it and give it like 10 minutes to see if the alerts will be locked. So we retrieve the cipher and we retrieve the key, and Rubius is executed, nothing detected on our GUI. So I will stop the video and come back like after 10 minutes or 13 minutes. I will come back after in 12:40 or 12:45. Now after around more than 15 minutes, we are in 12:45. So let's refresh the page to see if there is any log. After 12:23, because that was the last Rubius that we dropped. Alright, there is no alerts after 23 for the sharp loader, so we successfully bypass both static detection and behavioral detection because we patch ETW. AMD is relying on ETW for .NET information retrieving. That's probably how they got the signature in memory for .NET. And we bypass the static detection as well by loading the Rubius, by decrypting the Rubius and load it in memory using Cellar, and patching AMD as well, so that the assembly will not be scanned and we will get detected. Now let's take a look at the fourth way to bypass static detection by using the paid software VMProtect. So VMProtect is a software protection tool used to obfuscate and protect code from reverse engineering, debugging, and unauthorized copying. It achieves this by virtualizing the original code, meaning it converts the x86 and x64 instructions into a custom, highly obfuscated virtual machine language that only VMProtect can interpret. VMProtect converts the application code into bytecode for a custom virtual machine. The virtual machine bytecode and the virtual machine interpreter are embedded in the final protected executable without the need of additional libraries or modules. At runtime, the virtual machine interpreter decodes and executes the protected code layer by layer. Now let's take a look at the code of the binary we want to protect with the VMProtect. So inside the main, we have this payload, which is a Metasploit payload. It's statically detected. After compiling the binary, I will drop it to disk and you will see how it's got detected. Then we call virtual alloc to allocate a committed and reserved memory with protection read-write, the size of payload allocated memory. Then we check if the memory is valid, and we copy next the payload to that allocated memory using move memory. Then we call virtual alloc virtual protect to change the protection of that memory from read write to read execute. And after that, we create a thread that will point into the allocated memory to execute the shellcode, and we wait for this shellcode to termine the execution. So let's compile it and drop it to the MKTG machine. Alright, it's compiled. Alright, and drop it in the MDE machine. So here is the MDE machine. To check that, we run cmd and launch the PowerShell command to list some processes, security processes. So we press PowerShell sh execute this command, ps and check the core for Windows Defender, which is the core process for Windows Defender, which is MSMPENG, and it's running, and check the core process for MDE, which is MSSense, and it's running as well. Now let's try to drop the loader and see if it will get detected or not statically. Alright, it's detected, and the detection is Metasploit, I guess, or Meterpreter. Okay, the detection is Meterpreter. Now let's run vmprotect and try to protect our loader.exe. So let's drop it and do some vmprotect configuration. So the complexity would be 100%. I'm sorry if the font is very low, because there is no option here in the vmprotect to increase the font size. So the complexity is 100%. Rename it to new, maybe new.exe, the generated file, and the relocation to yes, strip relocation. All right, and in functions we add functions like the main functions. All right, how to include the main function, entry point. All right, and make the complexity for the main 100% as well. So let's compile it and generate obfuscated binary. I will come back whenever it's compiled. So the new.exe, the protected loader.exe is generated. Now let's drop it to the MDE machine to see if we can break the signature of Meterpreter or not. Alright, it's not detected statically on disk. Let's try if it could be detected in memory statically. For that, let's run it. And we got calculator popped up without any static detection on the memory side and on disk side as well. Now let's resolve the learning objective tree. First of all, we have to bypass the static detection by compiling our project with OLLVM. We will demonstrate that in our native malicious PE loading in the second task. Bypass the native malicious PE static detection with the .localhollowing projects, and we will demonstrate the loading of Mimikatz. After that, we will bypass .NET malicious PE static detection with CLR loading and bypass of IMZ and ETW by patching their memory. And the demonstration will be with seatbelt. Now stop the video and try to solve the solution and come back whenever you are ready. Now refer to the student's VM machine inside the evasion, see evasion tools LO3, and we will find the sharp loader and local hollowing folders. So access to the RDP to the MKTG machine from your student machine. Alright, and let's check if MDE exists and Windows Defender as well. So this is the core process of Windows Defender. It's running, and this is the core process of MDE. It's running as well. So let's go back to our local hollowing project and try. You will find Mimikatz. Try to drop it to this machine, the MKTG, and it will statically get detected before even we run it. Once we drop it to this, it got detected. and your machine will probably get isolated once Mimikatz is detected. If the machine isolation is enabled on that MDE configuration. So now let's get back to our folder, local Halloween. You will find it inside the LO3 folder, and generate the Mimikatz cipher and its key, ES key, and generate the headers for the arrays for those cipher and key, and replace those cipher buffer and the key buffer on the mimi.h. All right, now let's go to that location and generate using the Python script the cipher and key for Mimikatz, the ES1 version. So let's open Hex editor and drop both the cipher and key. Click on the cipher, file, export, and generate the cipher.c. Put it on the local Halloween directory, and do the same for key.bin and generate the C buffer and put it on the local Halloween as well. Now the last thing to do is to copy mimi.h into the previous directory and open it with Notepad. Alright, here is the mimi.h. We have to change the key buffer with our new key and the new cipher, the best cipher with the new cipher. So let's copy the key.c here and copy that key content and replace that with the new key content. And similar for the cipher.c, copy it to Notepad and copy the new cipher content to the mimi.h best cipher content. Alright, it's changed. It's save mimi.h. Make sure that the key size is 16 and the cipher size is similar to the one from Hex editor. It's the same. Now save mimi.h and copy it to the local Halloween folder by replacing mimi.h with the new version. Let's go back and open the local Halloween solution and build the project using CLang and OLLVM flags. Now, after opening the solution, I will be using the Visual Studio solution to configure the projects. In your case, you will using the build pipeline. So refer to the past video about the build pipeline usage. So I open properties and here we chose the platform toolset to LLVM. As well, I chose this run library to multi-threaded and the command line using LLVM flags. So I already compiled the code to generate this local Halloween.exe that contains the new version of Mimikatz, encrypted Mimikatz. It will be loaded in memory and map the entire sections, headers, and fix apply relocation, fix the import address table, and trigger the entry point. So I'll be copying that and see if it will be detected statically on disk like Mimikatz. So the static detection on disk is bypassed, not detected. So let's see if we'll get detected on runtime, on memory. And Mimikatz, it's running completely in memory and there is no detection on our side. So let's see the other demonstration. Now let's take a look at the second demonstration to run Silch build and bypass static detection using the CLR loading and the IMZ and HEW patching to load .NET malicious PE. So let's drop the Silch build on the target machine, the MKTG machine, and to see if Silch build will be detected or not statically. Once dropped, it got immediately detected. All right, now let's try to open a CMD on that directory to generate the RC4 cipher and key for SageBuild. So we run the RC4 on SageBuild and it will generate the cipher and the key. So let's copy them on the student VM machine. Let me open a CMD on the student machine to check out my IP. It's that. Now the last thing to do is to generate the base64 command line for this argument that I will be using, which is group equal system with a dash. All right, so this is the argument that I will be using. Now let's refer to the sharp loader project, and before that I already compiled it, so I will copy it on the target machine. In the sharp loader I'm using here just simple configuration for Visual Studio, and I'm using Microsoft Visual Studio compiler. I'm not using OLLVM in that case. So it will be a normal configuration because there is some C++ headers and syntax. It will not work for our OLLVM configuration. So I will copy the sharp loader in the MKTG machine. All right, and see if it will get detected or not. So the utility doesn't get detected. Let's run it to make sure it's not detected. So let's give it the arguments. The host is the IP of the student's machine. Right, and the port, let's set up the port on the student's machine. For that, let's open the AMD, go to the desktop, And let's see if there is Python here. All right, there is Python, and let's run python -m http server to run an HTTP server on port 8000. Now let's go to the tool and run 800 as port, and the key will be the key name .bin, and the cipher will be cipher.bin, and the argument is the generated argument that we generate before, which is that argument. All right, now let's copy the argument. And run the tool. So it's passed successfully the argument, and it's retrieving the cipher, the key first, the cipher, and it's running. As you can see, the SH-bit is running. There is no detection, static detection here, and it finished its result. So we didn't get detected as SH-bit get detected statically.